abstract and giving me the chance to give this talk. So I've really loved it. I think it's a fantastic event, and I've learned ever such a lot. So the only thing that went wrong was the weather at 9 o'clock this morning, right? But I don't think we can blame the organizers for that. Okay, so a bit of background on this work. So actually, this isn't really my main field at all. So I've worked for some years studying conscious perception, really, using rapid serial visual presentation, which some of you will be familiar with, and I'll clarify that in a minute. But at Canterbury, Kent, so I have two positions. I'm in psychology at Birmingham University and computing at Canterbury, Kent. And, you know, so I've done all this work on studying conscious perception and trying to understand, you know, we've even got a model of how humans consciously perceive, if you like, in these RSVP context. But, you know, the people at Birmingham find that interesting, but the people at computing at Canterbury thought, well, that's, you know, who's interested in that? So as a result, I've started to think about applications. So taking some of the work we did there with RSVP and also EEG, and then trying to come up with applications of that that might make my colleagues feel more disposed towards me. Okay? And for the UK people to do some impact, right? So we can get an impact case study out of this. Yeah, and we've actually developed a number of different systems. So we've got a paper on a brain-computer interface with a very similar method. But obviously, the most interesting and kind of emotive of these is a deception detector, and that's what I'm going to talk about. So as I say, when I started doing this, it was somewhat peripheral, but I think we've got something interesting. And so actually, I've run perhaps 10, 12 studies with different PhD students on this over the last couple of years. And so this is me trying it out in front of people who would know whether it's interesting. Okay, so I'm very interested to see what you think. Okay, so firstly, so this is me, this is me, this is me. Okay, so I'm going to start off with a demo of RSVP. And as you may not be surprised, I'm going to present you a load of names. Okay? So once I press this button, you'll get 5 fixation crosses in the middle of the stream. Just look at that, and you'll get a stream of names coming extremely rapidly at you. And I want you to just tell me when you see something that might be of interest. Okay? Here we go. Yeah. Okay, so that was an easy one, right? I've primed you. Okay? But did most people saw my name in that? Right. Okay, here's another one, exactly the same. Ah, yes. So a few people saw Nelson Mandela, right? Okay? So, but the point about that one, right, is I haven't primed you at all with that, right? That's just because Nelson Mandela is intrinsically salient to you. He's a famous name. I didn't mention famous names, and that's popped out of the stream. And just to say, each of these streams contains, if I remember rightly, 30 items, right? So that you know, you may not be aware of that, but there's loads of items that you're not perceiving at all, right? Because it's just coming so fast. Let's do another one. Yeah, okay, so you all got that now, right? Because of the famousness, you're away. Okay, so, oh no, let me go through those, sorry. Okay, so that's RSVP. Okay, and so RSVP has been around for ages. I think the first paper is Mary Potter in 1968 or something like that. And in sort of theoretical scientific investigation of attention, perception, it's been done to death. There's loads and loads of papers on it. But as I say, we're trying to take it and think about applications and think about it as a potential way to do what I now understand I should be calling the concealed information test, right? So just on the method, you know, what's going on? And this is kind of the critical point. So in a sense, what we're doing is we're bombarding the perceptual system with so many stimuli so rapidly that it just can't keep up, right? Okay? So if I slowed those streams down, the task would become trivially easy. But you know, in this paradigm, you're presenting these incredibly quickly, and it comes as this kind of jumble of stuff. So subjectively, it might just seem like a jumble of stuff. But the interesting thing is, what you consciously perceive from the stream is, if you like, the things that are salient to you. Okay, that's the critical point. So while it may just seem a jumble of stuff coming, actually the brain is doing something very selective, right? So in a sense, the brain is monitoring, if you like, pre-consciously, looking at all these items that are coming, and then when something salient is detected, that is presented to your conscious awareness, breaks into awareness, and you see it. Yeah, and so the point that each of those streams contained 30 items, but maybe at the end you might have been able to recall just 2 or 3 or something like that. And the interesting thing is it is the salient ones that you see. Okay, so this is just some data to sort of confirm that. Actually, I'm just going to talk about the one on the right. I haven't got much time. This is one of our studies, and this was letters in digits. So we've presented an RSVP stream of digits, and you just put one letter in it, and then you've got to report that at the end of the stream, at about the same speed as what I just presented. And what you find is you get an 82% accuracy on that. So reporting the letter at the end of the stream. And guessing would be tiny, right? Because there's 20-odd letters. So what that says is, okay, this is not quite the same as the concealed information test case, which I'll come to in a minute, because here you're giving them a task. You're telling them what to look for. But the point is, again, that 82% of the times you do see the letter and you're able to report it when you're looking for letters. This is actually the case, more the case I'm going to look at. So this will be effectively, when I talk about my experiments a bit later, the target or the fake, the performance on the target or the fake. So this is a stream of names, and we give the subject a name to look for, if you like, a target. Actually, in terms of the story of the deception detection, it'll be a fake. But think of it as a target. And then at the end of the stream, we ask you to say whether that stream contained the target or not. And the interesting thing is you get a hit rate of 93%, okay, of saying yes when it was in the stream, but also critically you get a tiny false alarm rate. So you very rarely say it was there when it wasn't there, okay? And if you put that all together and you do your signal detection, you get this enormous D prime of over 3, right? So that's all just making this point that the brain really is searching in this context, in these RSVP streams, and doing it very, very effectively, actually. Even though we're not aware of that going on, it is doing it, it's doing it effectively. Okay, so that's the first part of my story. The second part is EEG. Okay, so or strictly ERPs, event-related potentials. So again, this is one of our experiments, and just to orientate you, because maybe people are not too familiar with this, 0. So here's time, and here is literally voltage. Okay, recorded actually at an electrode PZ, which is kind of there. The critical stimulus that we're plotting, this response to, starts at time 0. Okay, so this is the electrical response following that stimulus coming on at time 0 and finishing just over a second later. Okay, and the important thing is that the black line here, well, that's what people will call a P3. Is that actually somewhat different to an oddball P3? So it's not quite the same as what other people have used in this context. But that's a P3, so an enormous positivity. So this is about as big a thing as you can see in ERPs, really. It's a very big positivity if you perceive the stimulus that was presented at time 0. Okay? So if you're able to report it at the end of the stream. And the red is basically when you don't get it right. You don't consciously perceive it. Right? So the critical point to make is you can think of the difference between the big black and actually really a little thing like that. Okay, so at this particular electrode PZ, that effectively is the size of the response you get if you don't consciously perceive it. Right? So it's tiny, it's nothing. But if you do consciously perceive it, it breaks into awareness. You get what people would talk about as a brain scale state. Okay, frontal lobe interacting with parietal lobe, and you get a whopping great P3. Okay? So the point is, in terms of ERP work, showing this sort of difference, if you can turn the deception detection problem into comparing whether you get this big P3 or you don't, you're really in business, right? Because there's a very big difference between the two. Different PhD students plot positives. Some plot it up, some plot it down. So here's positives up. Later it's going to be down, but I'll warn you. Okay? So it's the worst sin of anybody. Okay, there we are. And so as I said, those are the kind of background bits of story. RSVP, this highly selective aspect to it, and then secondly, the P3 and ERPs. So we've been trying to take those. Well, okay, one thing to say about that is that one aspect of this is you've got a very high bandwidth of presentation, right? Okay? So I presented 30 items to you in sort of 2 seconds. So potentially you can present loads of items to somebody, then record with EEG and find out which amongst those items did the person find salient in some very broad sense. Okay? So that's the nature of the method, and then we've looked at a number of different places in which you could use. And by the way, the American military do image triage with this, which if you want me to tell you about that, I can do in the questions. But the thing that I'm going to particularly focus on is this deception detection, and which I think is a concealed information test. Oh, sorry, that's the wrong one. Okay, so our first paper on this, which was out a couple of years ago, just demonstrates the basic method. And that's what I'm going to talk about. Now, I should say that, as our first approach to this, we did the easiest thing that you could do, and this has been discussed in previous talks. We just looked at people's own name. Okay? So we did, if you like, the most simple thing, we gave people a name to pretend was their name, which is a fake, or it's effectively a target. And then we also presented in these RSVP streams a probe, which was their real name. And then we also presented an irrelevant, okay, and this is where I think the story is interesting, what happens with the irrelevant. And we also presented an irrelevant, which is presented with, if you like, the same presentation statistics as the other items, so you can make a fair comparison. And critically, they're not aware of what the irrelevant is. Right? But it's coming as many times in the same sort of position in the stream. And obviously what we're interested in is comparing the response to the probe, and hopefully we're going to get a whopping great P3 for it, right? And the response to the irrelevant, and hopefully we're going to get pretty well a straight line for that. Okay, so this is the point. This is where I'm kind of asking the question of you lot, whether you buy this or not. So the potential reason why this is interesting, I should say people have sort of talked about this sort of thing before. So I think Rosenfeld has a paper with subliminal priming where he talks about this issue. But they don't use this particular mode of presentation, which I think makes it more effective. But the critical point is you might think, so what we're looking at with RSVP is, if you like, an implicit response, right? So the brain is pre-consciously searching. This is, if you like, in some sense, the subconscious brain that's seeing this thing, and then the floodgates open, it piles into awareness, and you consciously perceive it. So the argument would be somehow it should be harder for somebody to control that response, right? Because it is about, a sort of implicit, almost pre-conscious aspect of the way the brain works. And then you might think it's more difficult to apply countermeasures. Right? Because a countermeasure, by its very nature, is a conscious, volitional, task that you're going to perform. And the particular one that I will talk about, so in a later, and I'll show you this in our later experiments, we've done a number of different countermeasures, and the one I will look at is whether they can see the irrelevant and artificially elevate their response to it, which is a standard countermeasure that's broken previous EEG methods in some sense. Okay, so before that, I'm just going to go through this because I realize I'm already running out of time, as usual. So let's just power through this and just look at the basic finding. Yeah, we'll look at the basic finding. So, and then I'll just sum all the other stuff up. So this is our first experiment. So this is not the countermeasures. And we're looking at the ERP response to actually two irrelevants. For technical reasons, we put two irrelevants in here. They're the blue and the black. And what you see is they're effectively a straight line. You get this, what's called a steady state visual evoked potential, which is just each item of the stream setting up a small response in visual cortex. But the critical thing is that the fake or target is the big red one, and that's what you'd expect, right? Because they're looking for that. That's the target. But the interesting thing is the green one, which is the probe. So that's their real name. And so that's also generating a big response, and the critical comparison is between, say, the green and the blue. And in this context, in this experiment, it works beautifully. Okay, so I won't go through everything, but this is an experiment with 15 subjects where we look for significance in a statistical sense for each individual. Now, we actually look at 3 different electrodes, then we combine them together with this thing called Fisher combining, which I can talk to you about if you're interested. And then we run what's called a Monte Carlo permutation test. So some people have been talking about resampling. It's a resampling method. And basically, we get very small p-values for every individual. So you can think of these, say, take this p-value. This p-value is conceptually saying that there is a 1.7 percentage chance that this size of difference between probe and irrelevant would have cropped up if the person was innocent, right? Because the permutation test generates a null hypothesis, which is conceptually what would happen if they were innocent. And what you see is that all of the p-values are tiny, and we get 100% hit rate. Okay, so let's just go on from that. I'm just going to quickly say this is one of our countermeasures experiments. So we've got a paper called Countering Countermeasures, which looks at a number of different countermeasures. And this is in a sense the critical one, where we tell subjects there are irrelevants in the streams. Okay, and your task is to see them and to count them. Okay, and basically the upshot is it doesn't really change the ERPs very much, and you know, so the simple thing is that they can't see the irrelevant because they don't know what it is. So they can't search for it purely on the basis that it keeps coming back, right? Which consciously you can, right? So if I keep presenting stuff slowly to you consciously, eventually you say, oh yeah, you presented that before. So the point here is that's something that you can't do, or certainly can't do effectively, in this mode of RSVP. So you can only search for things you know what they are, in some sense. And just to say, here's, these are actually 4 different experiments with different countermeasures applied, and we get a high hit rate for all of them. I'm just going to quickly show you Innocence. Okay, so this is running people where where the probe is not their real name. Effectively, there are 3 irrelevants. And what you notice is that all the 3 just chug around here. So there doesn't seem to be an inflation of the false positive rate for Innocence. Actually, we calculate a false positive rate of 0.083, which should be 0.05, okay, given the alpha level. So there's not much evidence of inflation there. Okay, so that's the basic first set of experiments. I'm just literally going to summarize the next set. So obviously all of those were own name, right? And in some sense, that's the most exquisitely salient stimulus you could present. So as has been discussed earlier in this session, we then wanted to look at other sets of stimuli and see whether they also pop out of the stream in a similar way. So the first thing we did is to do 2 experiments, one with famous names and the other one with famous faces. You saw the famous names at the beginning, right? And basically, so those are not lie detection experiments, they're just to see whether whether the familiarity of the items causes them to pop out of the stream. And it does. So that's the response for, this is famous names. So the green, again, is the response to the famous name. And we didn't even tell them that they were there, right? Okay, so they just pop out. And again, probabilities work fantastic. Famous faces, so that's that experiment. We get this amazingly bizarre pattern. So we didn't expect this pattern in the ERP. So that's a response to the famous face. We thought it would be a P3. But anyway, it's still a massive effect, right? We apply our statistical analysis, time frequency, and look at these. You know, so almost all of these are as small as they could be with 1,000 resamplings. Okay, so final summary slide. So 2 more experiments we've just done, and these are preliminary findings, really. So firstly, with email addresses, so we present streams of email addresses, and we put their own email address in there, and look at the P3, and that's worked pretty well. We get a 70% hit rate for that. So not quite as high as the others, but still reasonably good, and we think we can improve it. We think we know how to do that. And then the final one was familiar faces. So, and by the way, these are both concealed knowledge tests. These are framed as deception detection experiments as well. So the familiar faces, we present to PhD students RSVP streams containing the face of their supervisor and the head of the research group and da-di-da-di-da. And we get 50%. So it's somewhat less, but we think we know why that is, and we think we can make it better. Okay, so that's the end. Thank you.
Any questions?
Thank you. I found it interesting that in the first iteration of showing to us, you showed us names, the 8 to 10
Right.
letters each. And then now you're moving to email addresses, which
Right.
is making the assumption of longer. So I was curious
Right.
what you think the absolute limit number of characters
Right.
would be. Because the research you're doing is machine learning.
Sure. So I think you know, you're absolutely onto the sort of issue that I think is very important. Just to say, with the email addresses, we just presented the front end of the email address. They were all from Birmingham University. We just gave the front end. So in a sense, it didn't crop up there. But absolutely, you're right. So in some of the experiments, we pad out, okay, to make all of them with pluses and crosses, to make everything of the same extent. Because here, you know, the masking is the critical thing. Each item is masked by the following item and a bit by the preceding item. So you want to try and control that and keep that regular. But I do think we have run some experiments which haven't worked so well, and I think they're related to what you're saying, that actually what could happen is that people could focus on just one part of the whole of the stimulus, right, for the target, okay, and not read the whole thing, and then the probe doesn't burst into awareness. So we particularly had that with an experiment with birth dates, where we did number, month, and they just looked at the number, right? But to know you're seeing your birthday, you need to put the two together. So I think there's lots of issues there about exactly how you present to the participant, to get them to, you know, so that they fully process the probe and it pops in. The other thing to say is there are these methods now. There's a company which does RSVP reading, okay, as speed reading. Okay, so you can read sentences in RSVP. And so 10 a second, you know, speed reading. But what they do, which is sort of interesting, is so they've obviously got exactly this problem. They've got words of many different lengths. And what they do is they don't present all the words starting at the same point. They shift them around on the screen. So they find the sort of optimal point in the word. I guess the position is where, you know, your fixation falls naturally in a word, you know, if I present that in an experiment. And they always have that in the same position. So actually the words are kind of coming around like this, if that makes any sense, right? But you're always keeping the optimal point for processing the word at the same position. So basically, I think you're right. Those sorts of things, exactly how you present, are critical. And, you know, we've already run into issues there, but not any that we can't overcome just yet. Yeah.
How do you set the screen speed so that the relevance are not visible to each subject, because there's a lot of individual variability in that regard?
Right. So absolutely. So with all these experiments I've talked about here, we just fix an SOA for everybody, right? But we do a lot of training at the beginning. So in fact, when they come in through the door, we first present them with an SOA of 400 milliseconds, and then we slowly, you know, titrate it down to make it faster and faster. And And you know, and we don't move on to the experiment proper until they're doing it relatively effectively. But I think you're absolutely right. You know, obviously the other thing about this is it's all just students, right? And actually, some of ours are computing students who are used to doing a lot of gaming, right? So they're very good with all this very fast stuff. But if you were to take a broader spectrum of individuals, you would have a problem, right? So I think if you particularly took an old population, the SOA should be a lot slower. But what you could do, now, in fact, we have done this in one experiment. You could do a staircase procedure at the beginning. Okay, so when you basically work out their perceptual threshold from their behavior in a pre-test. And you slowly move it, you know, you start with a long SOA and then you make it smaller and smaller and smaller, and all of the time you're working out, you know, how successful they are at seeing targets or whatever. And then, you know, maybe you make it too small and the performance goes down, and then you make it small, you work out and you set the SOA that's appropriate to that person, and then you run that in the experiment. So at least in principle you could do that.
But it's not adaptive. You want to experiment. It's not adaptive.
It's not. It's not at all, no.